Okay, now that we've talked about the gas laws, we must not forget gas laws are based on the kinetic theory. And the kinetic theory presupposes that if two molecules are colliding together, they will each retain their kinetic energy. That's called an elastic collision. For those of you who remember the metaphor, it would be like playing pool or billiards, and you're hitting the cue ball, and that cue ball runs right into one of the colored balls, and the colored ball doesn't do anything. The cue ball just goes careening off. Actually, if collisions are elastic, that cue ball will go bouncing off the walls and other balls for all eternity. But we know that we don't live in that world. We know that in the real world, energy is transferred from one object to another when things collide. So, in the real world, it is possible for molecules to collide in such a way that they actually stick together to form a liquid, but not in the ideal world, not in the world of the gas laws. So why do we even use the gas laws if they don't apply to reality? Well, the fact is that for the most part, we're talking 98% of the time, ideal gases act just like real gases. Under what conditions do they not? That's what we're going to focus in on today.
One of the things that teachers who aren't me tend to say is that you need to learn all this stuff because someday you'll be out there in the real world and you'll need to know how to do all the things that adults do. First of all, I don't really believe this because I think you should be learning just because learning is fun. But I also remember when I was a kid hearing that and thinking that this real world couldn't be that much tougher than high school because it was pretty tough. But looking back, I can tell you that life does indeed get a bit more complicated after 12th grade with jobs and bills and raising kids and taxes, and I haven't done any of the raising kids, but I've seen it and it looks really hard. And then there's always knowing that there's always more work waiting to be done. But the truth is, while it's more complicated, it's not really that much harder than high school. Most adults rarely have to take pop quizzes or final exams or ask permission to go to the bathroom, wear orthodontics, have a curfew, live on an allowance, find a date for prom, or shower in a room full of people that they don't like, all while trying to build your first real lasting relationships. Yes, real life is tough, but the ideal world of teenagers? Not ideal. Turns out that the biggest problem isn't so much that the pressure increases in real life, you just have to learn a few new tricks to deal with it. And the same goes for gases.
Yep, the same goes for gases. For the most part, ideal gases and real gases act very similar, mainly because gases are really far apart. So that if they collide, not only are they very far apart, but they have a lot of kinetic energy, so they're moving really fast. So they will collide. But when they collide, they will just go careening off. Yes, they will exchange a little bit of energy, but for the most part, they'll just go careening off in different directions. What do we call a gas that acts just like the kinetic theory? We've already talked about it. We call it an ideal gas. It's an imaginary gas. It's not a real gas. But for the most part, it acts like real gases. Under what conditions would a real gas not act like an ideal gas? Okay, like I said, gases are really, really far apart. So what would happen if we were to take this container and shove all those gases into a much smaller container? In other words, we would be increasing the pressure on them. Okay, so now if these guys are colliding 4 or 5 times a minute, since they have very little room here, they will be colliding many, many, many times. And every time they collide, there is a chance that they might just stick. But even if they do collide, they have so much energy that odds are that if they do collide and they try to stick, they have too much energy. They're like two hyperactive kids, and they're just going to just keep colliding. Okay, so what are we going to have to do to them as well as shove them close together? Well, What we're going to have to do is slow down the hyperactive kid. How do you slow down molecules? Decrease temperature. So if we get them super cold and shove them close together, increase the pressure, then what happens? They will liquefy. They will liquefy. They will act like ideal gases cannot act. So under those two extreme situations, real gases and ideal gases do not act the same way. Okay, so what's the big deal? Well, we're talking such extreme circumstances that these are things that we can only do under with very, very powerful instruments. So why would low temperature cause a real gas to not act like an ideal gas? Well, because you would slow them down. And when they do collide, they are more likely to not come away from each other. They're more likely to stick together to form liquids. Not only that, by increasing the pressure on them, you are shoving them closer together, and the closer they are together, the more likely that they're going to collide. So not only do they have to collide many times, but they have to be moving so slowly that they would stick when they do collide. All right. So you got it. Under those two circumstances, extreme circumstances that you just can't do in a laboratory unless you set about to do it. Under those two extreme circumstances, low temperature and high pressure, ideal gases and real gases will deviate in the way that they act. For the most part, ideal gases and real gases do act the same. All right, last target for this chapter. I can explain what molar volume is. We've looked at the variables of temperature, volume, and pressure. What variable have we ignored? That's right, the amount of gas. So you have an uninflated balloon. If you want to inflate the balloon at the same temperature and pressure, what do? You blow air inside. The greater the amount of air, and it's easiest, since we're talking about a bazillion molecules, it would be easier just to refer to it as moles of air. So as the moles of air increases, the volume of the air increases. That's assuming the temperature and pressure is kept the same. It was Avogadro. Well, actually, it wasn't Avogadro. He did a set of experiments that led his students and his grand students and his great-grand students to come up with these ideas. But let's give him credit, since he first came up with it. Avogadro's law states that if you have the same volume for three different gases at the same temperature and pressure, they will have the same number of molecules. Why? Because gases are very far apart. They don't interact with each other. Therefore, they're not going to react with each other. So it really doesn't matter what gas you're dealing with. It's going to act the same way. So it doesn't matter. We can get 20 guys in a room colliding against the side of the room. They are going to exert the same pressure as 20 girls. Yes, guys tend to be a little heavier than girls. It doesn't matter. All that matters is the number of gas molecules colliding. We can even get 20 chipmunks in the room colliding against the side of the room, and they would be exerting the same pressure, therefore they would have the same volume. It doesn't matter what you are. All that matters, according to Avogadro, is how many of you there are. So, how many liters can a mole, 6.02 times 10 to the 23rd, a mole of molecules take, how much volume can it take up? That volume is 22.4 liters. Now you might ask, of how much? Of what? It doesn't matter of what. It could be carbon dioxide. It could be oxygen. It could be helium. It could be hydrogen. Now, granted, the balloon is going to weigh different amounts, but as far as the volume of space that it takes up, it will all be the same because that volume is dependent on the number of molecules and not who they are. So any gas will take up 22.4 liters of space. Now, why is that useful? Because if you have a balanced equation, assuming that the temperature and pressure remains the same, then these numbers are relative to each other. That means that these numbers can be easily converted to liters. 2 liters of hydrogen plus 1 liter of oxygen forms 2 liters of water. And letting these numbers tell you the relative amounts of each is something that would become useful if you were to want to get deeper into chemistry and be able to predict how much gas you can produce from these reactions. Now keep in mind that these numbers tell you the number of moles, the number of molecules, and now you see that it tells you the number of liters, but remember what it does not tell you. It does not tell you the number of grams. You can't say 2 grams of hydrogen and 1 gram of oxygen will form 2 grams of water. No, no. Actually, you would have to say how many grams you have. If you would have to convert these to moles, and in 2 moles of hydrogen, you would have its formula mass times 2. 1 times 2. So that's 2 grams. You would have 2 grams there. 1 mole of oxygen, since oxygen is 16 and you have 2 of them, that would be 32. Will form 2 moles, you can't say liters, 2 moles of water, and water is 18, since we have 2 of them. 18 times 2 is 36. Okay, that works. 36 equals 36. But as you can see here, these numbers do not apply to these. That doesn't make any sense if you apply these numbers there. What this does is it validates the law of conservation of matter. So the 2 things we looked at here today is, number 1, we saw that real gases do not act exactly like ideal gases. But for the most part, they do. Under what circumstances will they not? High pressure, low temperature. The second thing we were able to figure out, thanks to Avogadro, is if you have 2 gases at the same temperature and pressure, and they even have the same number of molecules, they will be taking up the same space.